So our project was low temperature geothermal, and with the new advancements in technology, they actually use old air conditioning equipment to run a Rankine cycle on. So they just reverse the compressor and just run it as a turbine, thus creating power, thus making it a lot cheaper, more economical to produce power from low temperature geothermal water.
So part of the problem we found with controlling or with designing a combined heat and power system is controlling the system itself. There are two main loading conditions for a CHP system. One of them is producing enough electricity for the house, the other is producing enough heat for the house. And so what we wanted to do is do both. So we designed a control system that would basically take the user input, which is either plugging something into the wall, using electrical load, or changing the thermostat in order to maintain the house temperature. And what we found was that depending on what is more important, either producing electricity or producing heat, greatly affects the actual efficiency of the system. So basically what we have is user inputs is thermostat, which controls the inside house temperature, and the electrical load, which is modeled according to increased load during the day and decreased at night. And if you change the thermostat at any point, the system will work as hard as it can to increase the temperature until that temperature is maintained, and then it'll go back into its efficient operating mode.
Alright, we did campus wind power. Basically the project was to determine if it would be useful to put a wind turbine on Michigan Tech's campus. So we determined through these typical type maps of average wind speeds and power density and everything to determine how much power we could actually get from a wind turbine. Down here is charts of frequency of wind speeds, and typically we're usually in the lower end of what's ideal for a wind turbine. So you could get power out of it. The cut-in speed for some of the wind turbines is about 12 to 14 miles per hour or meters per second, and our average is about 6. So on average would be a little lower than ideal, but it's doable. What we found that the Michigan Tech actually uses about 36,000 megawatt hours per year, and the offset of one about 850 kilowatt is rated for at least for the Vestas 850. The output or the offset for Michigan Tech's power usage is only about 5 to 6%. So it cuts into it. It helps with the environmental issues as far as economics. So it's worth it in the long run, but you have issues of having a wind turbine in the middle of campus and also ice in the winter, and you know winters here about 8 months, so that's a long time that the wind turbine would have to be shut down because when it builds up ice, it's programmed to stop spinning, and you get ice falling down from the turbine blades.
We are here checking the economic feasibility of combined heat and power system over the conventional system, when we take electricity from the grid and the space heating requirements are satisfied by the natural gas fired furnaces installed at every houses. Over here we are using the exhaust of the micro turbine for getting the space heating and water heating requirements. So over a period of 25 years we have concluded from calculations that we'll end up saving $58,000. $3,20,000 is the cost required by a conventional system for a period of 25 years, and over here we are only getting $2,60,000. So eventually we are saving $58,000. 20 years is this break-even point. After that we'll start making profits. And this, the advantages of this system are it is more green. It emits only 1/10 of the NOx, which is emitted by a conventional system for 1 kilowatt hour. It emits less CO, and this system has a more efficiency. It's around 85%, whereas only 35% for the conventional system. And in Denmark and Netherlands, around 40% of the electricity capacity comes from CHP, whereas in USA there hasn't been an impetus to this system. There hasn't been enough education to the masses, so only 7% of the electricity needs come from CHP. But EPA and DOE are having an ambition to increase it to 14% up till 2010, which implies an addition of 50,000 megawatt extra to present capacity of CHP.
Okay, our project was to determine the feasibility of using ammonia as a fuel for vehicles. So we looked into 4 different areas. We looked into ammonia production, ammonia distribution and safety, extraction of hydrogen from ammonia because our vehicle actually runs on hydrogen. And then we looked into converting the hydrogen into mechanical energy. And we determined that you can, we were trying to replace a typical 14-gallon gas tank on the average sedan. So we determined that you can run it on just under 14 gallons of ammonia in your calculations.